Alright, so let's do this problem. Again, we want to construct the shear force and bending moment diagram for this guy. It looks initially like it's symmetric, but this force here is twice as big as that one. So the diagram will be shifted a little bit. So I'm going to start by assuming positive shear. I'm going to go ahead and call this point A. So I'm going to call that the shear at A. And then over here on the right side, this is going to be my positive shear at B. Now remember, on the left side, positive shear is up, and on the right side, positive shear is down. So it looks a little weird, but those are both positive shears. To help me with my equilibrium of the free body, I'm going to get a concentrated equivalent for this force. So I want the area under this curve. So it's 4 kilonewtons per meter times 4 meters. It's a rectangle, so that should be 16 kilonewtons. Half the distance, so whichever end I come from, it'll be 2 meters from this edge to the centroid. Now, so from that, I'm going to find my reactions. I have no preference, but I think I'll, just for change of pace, I'll sum moments about B and find my reaction at A first. You could also sum moments about A and find your reaction at B, either way, but I'll just do it that way. So I'll come over here and using right-hand rule for my sign convention, summing moments at B and making sure we're in equilibrium. So about B, the 4 kilonewton force, the 16 kilonewton concentrated equivalent force, and the 8 kilonewton force are creating what kind of moment about B, positive or negative? Positive. So I'll just take them in order. So I'll have 4 kilonewtons times its moment arm, which is just a meter. I'll have my concentrated equivalent force, which is 4 kilonewtons, times its moment arm, which is 1 plus 1 plus 2 is 4. Then the 8 kilonewton force, also positive, and that's going to be 1 plus 1 is 2, plus 4 is 6, plus 1 is 7. So that takes care of all the loading, and then I have the positive shear at A, which is about B creates negative. So that'll give me negative the shear at A, and its moment arm is 8. So what is the shear at A? 17 point, what'd you say? 15.5. Anybody else get that? I agree, 15.5. And that's kilonewtons. So I got a positive value, so I do have positive shear at A. I'm going to go ahead and sum forces in the y direction and use that equilibrium equation to help me find the shear at B. So just writing it the way it is, from left to right, I've got the shear at A up, minus 8 kilonewtons, minus 16 kilonewtons, minus 4 kilonewtons, and then minus the shear at B. So when I solve for the shear at B, what do you get? 11.5, negative 11.5. Is that what you guys get? 12.5. 12.5, sorry. Negative 12.5. So I now know that the shear at B is negative. So I know where to start, 15.5. I know where to end. So let's come over here and construct a template to help me draw my shear force and bending moment diagram. So there's my boundaries. What do we know happens at a concentrated... Yes, Mr. Stewart?
I think that should be 12.5 positive. Yeah, I think
No. It is not. You should check it. This should be negative. All this stuff is negative, right? And 12 is positive. So you end up with a big negative number here. And this is also negative. So this has got to be positive. This has got to be negative. The reaction is really up, right?
Yes.
But positive shear is down. So that's why you get the negative sign. Everybody see that? Is that a problem? Okay, so I'm going to assume, or not assume, I'm going to draw my positive x-axis, positive shear, and all my units will be kilonewtons. And from our reaction information, we know that we're going to start at 15.5 and land at negative 12.5. So let's see if we can make those things connect. We know from our work before that the change in shear between any 2 points is the area under the load curve. Oh, I've left off some important things here. I left off that, we started to discuss this. So what happens when we go from the left side to the right side of an applied force? What happens to our shear diagram? It changes abruptly, right? It steps up or steps down. So I know that's going to be an important point. So let me add that to my template there and there. And then you'll notice there's no load here, and then it starts again. So I need to add another line to mark the beginning of the load and the end of the load. So my template's a little complicated, but that should help us navigate this. So the change in shear is the area in the load curve. So I go up here under the first meter. What's my load? 0. So there's no change. So I start at 15.5. I am going to end at 15.5. And we know that the slope of the shear diagram, the derivative, is equal to the load. And what's the load in this section? 0. 0 load, 0 slope. So I have the first meter is constant shear. Now what happens is I go from the left side to the right side. How much does the shear change?
8.
It changes 8. Is that a positive load or a negative load? Negative. So that means it's going to go from 15.5, you're going to drop 8. Should give you about 7.5. The change in shear over the next meter is given by the area of the load curve. What's the area of the load curve from 1 to 2 meters? 0. So no change. So it stays 7.5. And the slope of that curve is given by the load. And the load again is 0. 0 slope, horizontal line. So it looks like over the first 2 meters we have kind of like a little stair step thing going. From positive 15.5 drops down to 7.5. Now what comes next? Well, the change in shear over this interior 4 meters should be the area of this part of the curve. Yeah, we've already computed it, right? It's 16. Is that a positive change or a negative change? Negative. So what's 7.5 minus 16? Negative 8.5. And what's the slope of the curve over that interior 4 meters? What's given by the load? And the load there is always the same value, constant, so a constant slope. Is that a positive or negative slope? Negative. So I'll have a negative slope that does this. So I have a triangular change. Now over this 1 meter section, the change in the change in shear is under the area of the load. And we go up and we look, what's the load there in that 1 meter? 0, so no change. stays 8.5. And the slope over that segment, well, again, equal to the load. We just discussed the load was 0, so 0 slope, so it's flat, little step. Now as I go from the left side to the right side of this load, how much does my shear change? 4, and that's what? A positive or negative change? Negative. So 8.5 minus 5 is 12.5. Looks like we're heading in the right direction. Now the change in shear here over the last meter is the area of that part of the load curve, which is 0. So 12.5 plus 0 is negative 12.5, so that worked out. And the slope of that curve is the load, and the load is 0, so I have a 0 slope. And you get kind of a inverted step section over there. So it looks like we did it okay. We matched up with what we started and what we ended. What else can we say? We know where the maximum shear looks like it is now. It looks like it's over here in the first meter, and it's 15.5. Now something's happened here. What's happened here? We went from positive to negative. That's an important point. So I'm going to add that point to my template. And I'm going to indicate that distance there, I'll call it x1. How can I find x1? Well, I'm going to propose that we use the same equation we've been doing all the time. And I'll propose it this way. I'll say the change in shear from this point to this point is equal to what? Well, it starts off at 7.5 and it drops to 0. So what's the change in shear? Negative 7.5. You see that? If simultaneously I project this line up to my load, that should be equal to the area in the load curve. So what's the area under the load curve on that same section? What's the area of a rectangle? Base x1, height 4. So that means that the area under the curve should be minus 4x1. You see that? Those things should be what? Equal. So that gives me an equation that says minus 4x1 is equal to minus 7.5, and you can solve for x1, which someone will have to help me. What is that? 1.875?
Yeah.
Everybody see that? So again, we're going back and using the same thing we did before. We're saying that will lead us to this, which leads us to that. Now, why did I need x1? Well, when I go to construct my moment diagram, I'm going to need to find the area under this part of the curve, so I'll need to know that dimension. So let's do that. So let's go ahead and find a positive x-axis, define a positive moment. We'll have units of kilonewton meter. What is the bending moment at A? 0. What's the bending moment at B? Also 0, right? External pin connections. So with that said, we can now apply our relationships that we've talked about. So the change in moment between any 2 points is the area under the shear diagram. So now when you're talking about area under the shear diagram, you can see why x1 was important, to be able to find that area. And then we know that the slope of the moment diagram, or the derivative, is going to be equal to the shear. So let's use those. So starting over the first section here, We know the change in moments, the area of the shear diagram. What is the area under the shear diagram here in this first section? Well, it's base times height. Base is 1 meter, height is 15.5, so it goes up to 15.5. And the slope of that curve is given by the shear, and the shear is positive, 15.5, and it's constant. So a constant positive shear looks something like that. So the actual slope of that line everywhere is positive 15.5. Now the change in moment for the next 1 meter segment should be the area under this part of the curve. What's that? Well, base times height, right? 1 meter times 7.5 kilonewtons. So that'll be 7.5. That's the change. That's a positive area. So what's 15.5 plus 7.5? 23? And the slope in that section is equal to the shear. And again, the shear is constant. 7.5, so the slope is a little bit lower. It's not as big. So it kind of bends down a little bit. That's not a bend. That's a constant slope to this point, and then a smaller slope to this point. I don't probably have it to scale, if you get the idea. Now, what's the change in moment over the next section, defined by the distance x1? Well, it's a triangle. And we know a triangle, the area of a triangle is 1/2 base, x1, which we calculated as 1.875, times the height, 7.5. So what's that? What's 1/2 base times height?
7.03.
So what's 7.03 added to 23?
30.03.
30.03. Basically 30. Now what's the slope of this line? How is this line shaped? Well, it's given by the shear. Well, the shear starts off as a positive value, but it drops to 0. So we know here that we've got a 0 slope. So the line will curve like that. It's a quadratic curve. That's why finding 0 shear is important. As you can see, since it indicates that you have a 0 slope in the moment diagram, you can probably already guess that's going to be our maximum moment in the beam. All right, let's hope that as we apply these same conditions to the right side of the beam that we end up at 0. So the next section will be this area. Again, it's a triangle, so there'll be 1/2 base times height. The base here will be 4 minus that, so that's 2.125. So 2.125 divided by 2 times negative 8.5 is? It should be somewhere a little more than 8. 9 something? Okay, that you need to subtract that from 30.03. What do you get? 21? So the change in these two was this area. And now the slope is given by the shear, and the shear starts off at 0 and increases to a negative value. So something like that. Again, it's a curve. From 0 slope to a negative slope. Now the next section, this 1 meter section, the change in moment is the area under this part of the load curve. Well, that's 1 meter times minus 8.5. So what's 21 minus 8.5?
4.5.
I've got this, don't have this thing to scale. And then we also know that the slope is equal to the load. You see the load is constant and negative. And then the last segment, again, the change in moment is the area under the load of the shear curve. That's a rectangle, base of 1 meter, minus 12.5, so that does bring us to 0. And then the slope will be constant and negative and a little steeper than before. So we've got a linear segment into a second linear segment into a quadratic segment, a third linear segment, and then a fourth linear segment. So let me ask you this question. What is the maximum moment in the beam? 30.03. Where does it occur? So from A, it would be 1 plus 1 plus, so it would be 3.875 from A. So now you can tell me exactly where the maximum moment occurs and what its value is. Mr. McBride, you had a question. Did you raise your hand? Change your mind? Mr. Stewart?
So when we have a question like that, we have to actually tell where that moment is?
No, it's right there on the graph. But it would not be, like say an FE exam or something like that. They could give you a graph like this or ask you to choose, and they say, where's the maximum moment? So I just want to see if you can read the graph. But if we were working this problem as part of a reinforced concrete design or a steel design problem, the max would count, and its location would count for reinforced concrete. Reinforced concrete will allow you to change your reinforcing based upon when the moment drops below certain minimums. So you might have to extend your reinforcing the entire length of the beam. So it would have a usefulness. Any questions about that one? I like that one. I would have to say that that's very testable